All right, guys, welcome back. This is going to be our 9.4 instructional video. And today we're going to start off with an example. A wildlife study is designed to find the mean weight of salmon caught by an Alaskan fishing company. As a preliminary study, a random sample of 50 freshly caught salmon are weighed. The sample standard deviation of the weights of these 50 fish is standard deviation of 2.15 pounds. How large of a sample should be taken to be 99% confident that the sample mean X bar is within 0.2 pounds of the true mean weight mu. A lot kind of going on there, okay? But I want you to take a second and see, even though you haven't quite learned it yet, see if you can figure out the answer to this problem. Again, what's the question asking? How large of a sample should be taken to be 99% confident that the sample mean is within, this will be important, within 0.2 pounds of the true population mean? Well, at this point, hopefully you've given it a shot and you gave it your best. We'll come back to solving this problem in a second, but let's get some ideas for this section. Most researchers, when designing an experiment, have a level of error and confidence level in mind. However, the next thing they want to do is identify what sample size they need to use. To give you a little bit of backing for what 9.4 is all about, is sometimes we are able to control and we have the ability to influence what sample size we want to take, okay? Now, obviously, there's a kind of tug and pull there, right? It's too impractical to not take a sample and just survey the whole population. But if we take a sample size too small, we worry maybe about the accuracy of our sample representing the population. The bigger the sample size, the more accurately the sample represents the population. So there's that fine line there where it's too difficult to take too big of a sample, but if we take too small, there's no point in doing that because it's not going to accurately represent the population. And again, sometimes we can control the sample size. Now, let me pause there. We can't always control the sample size. Think back to the prehistoric miniature horse example we did at the beginning of 9.2. The archaeologists can't control how many prehistoric miniature horse bones they find. If they only find 7 shoulders, and then we're taking the average of that shoulder height, so we have a sample mean, from a sample of size 7, they found 7. That's it. You can't magically find more, okay? You can't say, archaeologists work harder and get us a sample of size 50 because that's ideal. No, but in other situations, as we're going to see here, there are cases where we certainly could get a bigger sample size. Catching salmon, for example, okay? You can catch more fish. It'll take more time and effort, but it's a feasible thing. So when we can get a larger sample size, when we can control what the sample size is, what it allows us to do is set a margin of error. And that's what we're going to talk about. The goal of this section is to look at confidence levels a little bit differently. Instead of identifying the error, given the point estimate, that being the sample mean or the sample proportion, sample size and level of confidence, and make sure you write down what's in red, we will identify what sample size we want to use given a specified point estimate and level of error. So here's kind of the idea. If you're rolling stuff around in your brain, here's the picture, okay? We learn to this point, how do we find a confidence interval given a certain sample size and given a point estimate, whether that be the sample mean or the sample proportion, and a sample standard deviation. And using those pieces of information, we constructed confidence intervals with different levels of confidence, okay? Let's say, to give you an example, let's say we had a sample proportion. And what we did with that sample percent is we created a 99% confidence interval. And we came up with a confidence interval and interpreted it and said, we are 99% confident that our interval 22% to 88% contains the true population proportion of whatever we're studying. Do you see a problem there? Our 99% confidence interval, and what we've done to this point is we've had no control over how big the interval is. You see, in the example I just gave, 22% to 88% is a massive interval. Maybe the true population, if it theoretically, with a 99% level of confidence, we're saying the population proportion lies between our two values. So that means the population proportion could be 50%, or it could be 23%, or it could be 87%. That's a huge interval. That interval, frankly, while we have a 99% level of confidence in it, that the true population proportion is somewhere contained in our interval based on our sample data, unfortunately, that interval doesn't do much for us. It doesn't really help us out because the interval is too big. You see, the smaller the confidence interval is, the more useful it is. It's much more useful to say there's a 99%, with a 99% level of confidence, the true population proportion lies between 53% and 56%, than it does 22% to 88%. That 53 to 56% is something, okay? So here's the big idea. When we can control our sample size, we also then, or what we can do is when we can control our sample size, it allows us to set a margin of error. In other words, we can control how wide our confidence interval is by fluctuating how big our sample size is. And we're going to see more of that here in a second. So let's get somewhat practical with it. And I want you to think back to how did we find error in 9.1? Go ahead and flip in your notes. See if you can find the section where we talked about error, our margin of error in 9.1, and copy it down. Well, what I hope you found was that in 9.1, we found our error, the value that we added and subtracted to our sample mean to get our confidence interval bounds. We found that error by doing the critical value times the population standard deviation divided by the square root of the sample size. Okay, we had a sample size. We either had the population standard deviation or we substituted S in for sigma because in 9.1, as well as here, we're working with large samples. And we found our critical value by using the standard normal curve. Okay, again, because we were working with large samples. But the question is, and that what we're talking about here in 9.4 is we already have a level of error in mind. We already know this. We have a level of error in mind. Okay, we want to keep that interval small, so we're going to know what level of error we want. Well, can I still make the confidence interval? Sure. I just need to be able to control what the sample size is. In other words, what we're doing in 9.4 is instead of calculating error to create confidence intervals like we did in 9.1, 9.2, and 9.3, here we're going to know the level of error, and we're going to find the sample size we need to make that level of error in that confidence interval happen. But first things first, how are we going to do this? Well, if this is our formula for error, it was great because what we were doing is we were trying to find error in 9.1, 9.2, and 9.3. But here, we're not trying to find error anymore. We're trying to find the sample size given a level of error. So our equation needs a little bit of reordering. We can do that through algebra. So let's try and get n by itself. We can do that by dividing by z of c. And then, applying a little more algebra, can multiply across. And I'm trying to get n by itself, so I'll divide both sides by e now. And then, to get rid of the square root, according to algebra, I can square both sides. And we find that when we were estimating the population mean via a confidence interval, and we're working with large sample sizes. Again, that's a criteria here. Got to be working with large sample sizes, which means this n value is going to have to be bigger than 30. Then what we can do is we can reorder our error equation so that if we have a level of error, we can find the sample size we're looking for. Okay? Again, this is for when we are estimating the population mean with large samples using a confidence interval. Okay, this does not apply when we're working with very small sample sizes or when we're working with a population proportion. We'll get to that in a bit. So where do we practically see this in a problem? Well, let's go back. Now that we have some context, this probably makes a little more sense. If we look at it again, they're trying to find the mean weight of salmon caught by an Alaskan fishing company. We had an initial study that found the sample standard deviation to be 2.15. We're trying to find how large of a sample should be taken. They are 99% confident. And if you would, pause the video right now. Go ahead and find that critical value for a 99% level of confidence. Okay, now that you've done that, you'll know that it comes out to be 2.58. Again, you should have done that using your inverse norm. If you are not sure how to do that, refer to your notes or previous videos that we've done. Look back at the 9.1 instructional video. And they tell us that we want to be within 0.2 pounds of the true mean weight. In other words, our level of error needs to be no bigger than 0.2 pounds. Okay? What this is saying is if I calculate the sample mean for this random sample of 50 fish, you would tell me if I was calculating a 99% confidence interval that I'm going to add and subtract some level of error to my sample mean and I get my confidence interval. But what we're saying is we want those bounds to be no bigger than 0.2 above the sample mean and 0.2 below the sample mean. Okay? No bigger. So what that's going to require us to do is have a certain sample size. And we're trying to find that sample size so that we can make that happen. Again, a lot of this you could, if you want a practical example, you could have seen this in 9.3, question number 9. We saw that when the sample size got bigger, that confidence interval got narrower. So when we can control the sample size, we can limit how big our margin of error is. So specifically, to calculate that sample size, we use our formula that we just discovered. That was initially based on our formula for error. And when we reworked that, we found that n was equal to z of c times sigma divided by e squared. So we plug in our values. Z of c is 2.58, our critical value for a 99% level of confidence. We don't know sigma, but we do know s, and again, because we are working with large sample sizes, we are A-OK to substitute S in for sigma. That was our first definition in 9.1. Our error is 0.2. And when we plug this in the calculator, what we find is we get 769.2. 769.2. Practically, what does that mean? Well, this is the minimum sample size. This is the sample size I would have to use if I wanted to create a 99% level of confidence that only went 0.2, had a level of error that only went 0.2 above and below the sample mean. If you wanted to create your confidence interval and said, I only want to add 0.2 to my sample mean and take away 0.2, we want that error to only be 0.2, then your sample size has to be at least 769.2. Now, you all know we can't only catch 0.2 of a fish, so how are we going to round? Well, traditional math would say, hey, round down, but here we actually need to round up to 770. Again, why do we need to do this? Well, if 769.2 is the cutoff for this is what the sample size has to be to get that error of only be 0.2 on either side. We learned in 9.3, number 9, that as the sample size gets bigger, that confidence interval gets more accurate. It gets smaller. Problem is here, if I round down, I have slightly decreased my sample size, possibly making that interval just a little bit bigger, which could push me outside that 0.2 above and 0.2 below. So just to be safe, always round up. Why? Because it'll make our confidence interval a little bit narrower, making sure we're inside that margin of error that we want. In this case, 0.2 above or 0.2 below. So what we would say here is we need a sample size of 770 at least if we want our confidence interval that gets produced from our sample data to have an error of no more than 0.2 above or below the sample mean. Okay, let's try another example. A certain company makes light fixtures on an assembly line. An efficiency expert wants to determine the mean time it takes an employee to assemble the switch on one of these fixtures. Preliminary study used a random sample and found that the sample standard deviation was 78 seconds. How many more observations, it shouldn't say more, it just should say how many. How many observations are necessary for the efficiency expert to be 95% confident that the point estimate X bar will be off from the true mean by at most 15 seconds? Now, this last sentence might seem confusing to you, but all we're saying here is we want to produce a 95% confidence level, or a 95% confidence interval. We know confidence intervals have this form, right? We're trying to estimate the population mean. We can't find it exactly, so we come up with an interval that we are 95% confident in. What this is saying is they don't want this error to be more than 15 seconds. Either way, okay, whatever that sample mean value is, they want to make sure that error doesn't get bigger, doesn't get wider than 15 seconds. Okay, which we can control by messing with the sample size. Okay, so how are we going to do this? Well, we know our sample standard deviation is 78. Again, pause the video and take a second to calculate your critical value for a 95% confidence level. Okay, you should have come up with 1.96. And we want our error to be no bigger than 15 seconds. Well, according to the formula we learned, we want to find that minimum sample size. What we do is we take our critical value times our population standard deviation, which we don't know, but as long as our sample size is bigger than 30, we can use the sample standard deviation divided by our level of error. And when we do that, we get 103.9, which of course we have to round up. Okay, we got to increase that sample size to make sure we fit within that margin of error. And we get 104. So how would we answer the question? We need to do 104 observations in order to be 95% confident that our sample mean is off from the true population mean by at most 15 seconds. Okay, somewhere in, if our sample mean was 30, right? If our sample mean is 30, we don't want our confidence interval to be bigger than 45 to 15. Okay? We want to, whatever our sample mean will come out to be, we don't want to be going, our interval to be going more than 15 above and below that sample mean. We want that error level to be 15 or under. So in order to do that, you would have to use a minimum sample size of 104. And of course, if you use the sample size bigger than that, the interval will be even smaller. Okay. So using the same tactics, we can do the same thing for 9.3. Okay. We can find the sample size we need to get a margin of error. If we set a margin of error, say I don't want to go this far above or below the sample proportion. 9.3 is all about working with the binomial distribution and estimating our population probability of success. We can apply those same tactics. And if we have a margin of error and we don't want to be more than this far above or this far below added to this and subtracted from the sample proportion, we can control the sample size and do the same thing. Again, using the same logic, our error in 9.3 when we were working with large samples was z of c times the square root of p hat, it's q hat divided by n. Again, we're assuming here that we're working with large samples, otherwise we wouldn't be able to use z of c. So we need our sample size, We obviously would say we would want to do n times p is greater than 5 and n times q is greater than 5, but we don't know p and q. So as long as n times p hat and n times q hat, the estimates for p and q respectively, are bigger than 5, we are okay to assume the binomial distribution is normal. So as long as we are assuming those conditions are met, in other words, we're working with large sample sizes, so that we can solve these problems. Okay? Well, if we rotate this equation around using algebra, and I'm not going to show you the algebra, it's a little bit more complex. If you would like to know how it works, I will happily show it to you, or try it on your own. But if we want to isolate n, right, we're trying to find our sample size. It turns out the formula for that, after applying algebra to the formula we already know for error when we're working with confidence intervals for proportions, we get that n equals p hat times q hat times the standard that's not correct, times z of c divided by e squared. Again, you can it's basic algebra. Just gets a little messy with all the letters to get from our error formula to what's the minimum sample size. So, but if you want me to show you that sometime, I will happily do so. Otherwise, this is the formula we're going to use. Now, what we need to keep in mind is sometimes we will not know p hat and q hat. So if we don't know p hat times q hat, we will assume p hat times q hat is 1/4, or 0.25 if you want it in decimal form. Again, we won't always know p hat and q hat when we're trying to come up with minimum sample size. And if we don't, we will use p hat. We will assume p hat times q hat equals 1/4 or 0.25. Again, the logic here being the largest value that p hat and q hat can be when multiplied together is 0.5 times 0.5, which equals 0.25. Okay? It's the largest it could be. So if we don't have a preliminary study, again, we want to overestimate with our sample size. That way we ensure that our sample size is big enough to be in whatever interval we want, depending on the margin of error we're looking for. So to overestimate that for sure, to not underestimate it, because p hat times q hat, the bigger that is, the bigger your sample size is going to be. So to overestimate that, we will assume that p hat times q hat equals 1/4. Again, that goes back to the fact that that is the largest that can be, being if p hat was 0.5 and q hat was 0.5. Okay, so let's solve a problem. A company is in the business of selling wholesale popcorn to grocery stores. The company buys directly from farmers. A buyer for the company is examining a large amount of corn from a certain farmer. Before the purchase is made, the buyer wants to estimate P, which is the probability that a kernel will pop. Suppose that a random sample of N kernels is taken and R of those kernels will pop. The buyer wants to be 95% sure that the point estimate, whatever sample probability he uses, will be an error less than 0.01 either way. Another way of thinking about this, we got a guy who's buying all this popcorn kernels. And obviously it's impractical for him to go pop every single kernel, because then there'd be no product. But he wants to be 95% confident that whatever his sample probability is when he does a sample of the corn popping, he doesn't want the true probability of a kernel popping to be more than 1% away from his sample proportion. Okay, he wants that distance between the sample proportion and the population proportion to be less than 1%. And he wants to be 95% confident of that. Well, we can work with that. We just have to determine the sample size the buyer needs to use so that that interval is less than 1% either way. So how are we going to do this? Well, how large of a sample should the buyer use if there is no sample to go off of? Well, our formula for coming up with the minimum sample size needed when we're working with proportions is p hat times q hat times z of c over e squared. Well, we don't know p hat and q hat since there is no sample data to go off of, according to our first part. So we assume it's 1/4. Again, this goes back to the highest value p hat times q hat could be is 1/4. And we want to overestimate here our sample size so that we are for sure within that 1% margin of error. So we do 1/4 times our critical value, which again, our critical value, you can calculate this on your own, but the critical value for a 95% confidence interval is 1.96. We want to be an error at maximum of 0.01. And that all squared. And when you calculate this, you will get 9,604. He needs to use a sample size of 9,604 kernels and use that as the sample and find p hat out of that to meet the specifications of being 95% confident that the sample probability is no further away from the population probability. The difference between the two is no bigger than 1%. In other words, if you calculate your sample probability p hat and you add or subtract that level of error to it, that level of error is no bigger than 1%. In order to ensure that error is no bigger than 1%, what we're adding and subtracting from p hat to make our 95% confidence interval, your sample size has to be 9,604, at least. Well, let's say a preliminary study was done, and p hat of that preliminary study was 0.86. Now, how large of a sample should the buyer use? Well, this changes the game, because now we know p hat and we know q hat. Again, our critical value 1.96, our error of 0.01. And when we calculate this, we find, again, through rounding, make sure you always round up, that we would only need a sample size of 4,626 to ensure that we are 95% confident that the difference between our sample proportion and population proportion is less than 1%. In other words, to ensure that the margin of error that I'd be adding and subtracting to my sample proportion would be no more than 1% at a 95% level of confidence, got to have a sample size of 4,626. Guys, thanks for watching. You are good to go practice 9.4 now. Again, if you have questions, please let me know. I'd be happy to help.